Hello everyone and welcome back to our quantum optics series. In today's session, we will delve deeper into the fascinating interplay between atoms and electromagnetic fields. Specifically, we will focus on the transition dipole moment, exploring its real and imaginary components and what they signify in quantum systems. To bring these concepts to life, I will walk you through two examples that illustrate the nature of the transition dipole moment in practical scenarios. Finally, we will bring it all together by discussing the complete Hamiltonian for the atom-field interaction, an essential framework for understanding light-matter interactions. This lecture sets the stage for exploring phenomena like absorption, emission, and quantum coherence. So let's jump into the concept of the transition dipole moment. We discussed in our previous lecture that there are two kinds of dipole moments that could arise in the atom. That is the permanent dipole moment, and that is inherent of property of the atom, and the transition dipole moment that arises due to the transition of the electron between two energy levels. So we also see that it could be real and imaginary. So for the real part, it could be real because of the no, zero difference of the magnetic quantum number between two states, as the two orbitals have azimuthal symmetry and their uh, orbital angular momentum have the same value and projection along z-axis, and it is imaginary for the case where there is a non-zero difference between the magnetic quantum number, and it gives rise to the magnetic dipole dipole moment along x and y axis. And we will discuss these dipole moments and how they differ in the two cases with the help of two examples. So let's discuss the first example, and we will discuss this with the help of atomic hydrogen atom. So consider we have excited and ground state, and they are described as state 100 and 210 in the case of hydrogen atom, where 100 and 210 are respectively describing the quantum numbers and LM. And we could see that there is no difference of the magnetic quantum numbers between these two states. So it will give rise to the dipole moment that is along single axis and linearly polarized, and we will see that it comes out to be a real quantity. So the explicit form of these states is given in equation 2, as we could see that both states have no azimuthal uh, dependence, and has, in other words, have no phi dependence, and where n is given as the normalization factor. So in order to calculate the transition dipole moment, we have to take the expectation value of the dipole operator for the two transition states, that is the ground state and the excited state. And for the case of the atomic hydrogen states, it changes into the integral form. So we could make use of the spherical symmetry of the problem, and we could introduce the volume element in terms of the spherical coordinates, and could resolve the r vector, the position vector, the into the three axes, the x, y, and z axis, and further simplifying and expanding the integral by putting the x, y, z in terms of the spherical coordinates, and we can end up with the equation in 5. So this is a quite daunting and complex equation, and you may be wondering how we will solve this kind of integrals, that is the triple integrals along r, theta, and phi direction. So again, we could make use of the symmetry here, as we could see that the x and y, the phi dependence on along x and y. So we could see that this ends up to a zero integral with respect to phi along x and y axis. The only angle, the only integral survives along the z-axis, and we could see that it has 2 pi value. And we could generally see from this from these integral and symmetry simplification, we could see that the dipole moment has only direction along one axis, and it turns out to be a real dipole moment. So simplifying the other integrals along r and theta direction, we could see that the final dipole moment has that form, as we could see it is a real quantity and is linearly polarized along the z-axis. Similarly, to depict the case 2, where the difference between the magnetic quantum number of the two states, and we are making use of again the atomic hydrogen atom and its two state, the was state 100 and 211. As you could see that there is a plus minus 1 difference between the two states of the atom plus minus difference of the magnetic quantum number between these two states. So the explicit form of these two states for the hydrogen atom case is given in equation 9. So we could see that there is a phi dependence on uh, of the 211 state in that case. So we will see that how it goes and how it goes in our problem, and play a significant role in solving the integrals. So again, exploiting the spherical symmetry of the problem and taking the integrals, triple integrals, and taking and converting the integrals in form of the spherical uh, coordinates. So we could see that the integral along the z-axis is going to be 0, uh, as you could see in equation 11. But the integrals along the uh, x and y axis is non-zero, because there is a double phi dependence, that one is due to the phase and other is due to the cos and theta, cos and sine terms. So evaluating other two integrals along r and theta, we end up with that with a form in as given in equation 12. So we could see that the dipole moment in that case is circularly polarized along x and y axis, and it has two components, the real components and y components. So this is for the case where is the difference between uh, a magnetic quantum number between the two states, and there is a lack of azimuthal symmetry for the two state energy levels. So we will discuss the case of the atom with which has zero permanent dipole moments, so only the transition dipole moments term survive, and the magnetic and the dipole moment in that case is given in equation 13, and we will see that how it plays in the atom field interaction and the form of the Hamiltonian that we are going to discuss in the later slides. So we know that the total Hamiltonian is composed of three main terms. That is the system term, that is the term related to the atom, and it is given in equation 15 in terms of the in terms of the population operator. And the second term is related to the field, and field is our uh, electromagnetic field, and we know that uh, we uh, we discussed it in many number of times that it is just a harmonic oscillator, and the field Hamiltonian is given as the Hamiltonian of the harmonic quantum harmonic oscillator in equation 16. So our task is to find the interaction Hamiltonian, that the Hamiltonian rising due to the interaction between atom and the field. So we know that when the dipole interacts from classical electrodynamics, that when the dipole interacts with electric field, it has form as the dot product form and between the dipole vector and the electric field vector. And if we take its negative, we get energy of the interaction. So we also know that the electric field and has two main components, the plus component and minus component. So equation 17 gives rise to that. So we could see that electric field written in terms of the accretion and annihilation operator. So this gives us the plus and minus terms depiction. So expanding the dot product and taking the dot product of the dipole vector with the polarized vector polarization vector of the electric field, we came up with equation 18. So we have to put the normal and the conjugate form of the dipole vector in equation 18, and we could see that uh, the jump down operator has conjugate is equal to jump up operator, and jump down and jump up operator conjugate has equal to uh, jump down or conjugate has is equal to the jump up operator. Similarly, for the jump up operator, its conjugate is equal to the jump down operator. So putting these values from equation 19 into equation 18 and expanding the dot product, we came up with equation 20. So we will simplify our problem by assuming that two states have no difference of magnetic quantum number. So the transition dipole moment are real, and we could see that we have make use of this fact in equation 21. So further simplifying our problem by assuming that the dipole or the transition dipole moments have the same value and the same direction in going from excited to ground state and ground state to excited state. So we make use of this fact and take out the common term out of the bracket, and this comes up with the equation 22. So we could see that the square root term and the term in the small bracket is given as the coupling constant, and it gives us the measure of the strength of the interaction between a two-level atom and an oscillating external field. So when the external field is matched and strongly coupled with the two levels of the atom, the electron oscillate between these two levels with a well-behaved manner and with a specific period. So we could recognize this term as a coupling constant. So putting this term in this notation into 23, and we could see that we have four terms. So let's discuss them one by one. So the first term in the square bracket is the s minus the uh, jump down operator or spin down operator and the annihilation operator. And we could see that it does not make sense, any kind of sense, and we called it energy non-conserving term because C s minus denoting the phenomena of the trickle down of the electron going from the excited state to the energy to the ground state. And we know that when the electron goes from jump down from the excited state to the ground state, it emit a photon. But in that case, the creation operator is saying that it is absorbing uh, the photon, and it contradicts the usual explanation of the emission of the photon when an electron goes down from excited state to the ground state. So this is a non-conserving term. The second term is as plus and the annihilation operator, and it makes sense. And It makes sense as it is describing the phenomena that when an electron jumps from the from the ground state to the excited state, it absorbs the photon, and it is an energy conserving term. The next term is describing the phenomena that when an electron jumps from the ground state to the upper state, it creates a photon, but it contradicts the usual explanation uh, of the spontaneous emission. So it is also a energy non-conserving term. So the last term is depicting the phenomena when then an electron jumps back to the ground state from the higher state from the higher excited state and emitted a photon. So it is also a energy conserving term as it gives the physical meaning. So we will apply our rotating wave approximation into equation 23. So we will ignore the no energy non-conserving term uh, in equation 23, and we come up with equation 24. So putting all the pieces of the puzzle, the Hamiltonian of the atom, Hamiltonian of the field, and interaction Hamiltonian in the rotating wave approximation, we come up with the equation 25, and it is called Jaynes-Cummings model, and it describes the overall atom field interaction and the dynamics of the system when an atom interacts with the external field. So today we explored the real and imaginary components of the transition dipole moment, understanding their physical significance in quantum systems. Through two examples, we saw how these components manifest in atomic transitions. Finally, we introduced the complete Hamiltonian for the atom field interaction, providing a comprehensive framework to describe light matter interactions. These concepts are crucial for analyzing phenomena such as spontaneous emission, absorption, and stimulated emission, which are fundamental in quantum optics. Thank you for watching. In the next section, we will dive deeper into light matter interact coupling and quantum transitions. Don't forget to like, comment, and subscribe to stay tuned. See you next time.